Exploring more about asymptotic performance in Introduction to Algorithms, we have seen that asymptotic performance, what do we mean by this? How does algorithm behave? When the problem size gets large, we are talking about very large, with respect to the running time and the memory and storage requirements. So we have already agreed that we will use some model and there are certain things which are related to it, that all memory equally expensive to access. There are no concurrent operations on instructions which we assume to be reasonable. They take a constant or unit time, one order of one. And whenever function call is there, we'll talk about that. Then constant word size, that means it will be for every instruction. We have the word size as constant. We have also seen that for running time, the number of primitive steps that are executed, except for time of executing a function call. In this case, I will tell you what we are going to do. And any other thing, some specific things we'll talk. And we have also seen that why we are concentrating on worst case rather than this average case, and we haven't talked about best case yet. Just take an example. This is a simple insertion sort. Now, as I suggested that this course is basically on algorithm design and analysis of algorithm, not on data structure. So I hope that you are aware of insertion sort. Just to give you a glimpse that insertion sort is, just like the way you play cards, you insert value in a proper position. So if these are values, you place a value in its correct position. You insert a value. This is how insertion sort works. This is a part of a algorithm which is taking part insertion sort. That is from some value to n. We have some value key, and then we start j with I minus 1. That is the value which is coming from I. We start a value which is less than I. One number less than I. That is j. And then while this j is greater than 0 and this key, this aj is greater than key, we do following swapping and again reducing j and then assigning key to aj plus 1. So what is happening? Just take an example. If you are not aware of this, let's take an example. You will be more comfortable with this. There are certain values 30, 10, 40, 20. They are not arranged properly. Means they are not sorted. Now we would like to sort them. I is, all these value I or j or key or aj or jth value of array A or j plus 1 or next value of A, array A. They all are this. We don't know them. So we assign them as null or empty or zero, depending on the programming language. So what happens now as we move along? If this is 1, 2, 3, 4, these are 1, 2, 3, 4. What happens here is now I has a value 2 because it is starting from 2. So I has value 2. And what about j? J will have value I minus 1. That is 2 minus 1. J will have value as 1. So I has value 2. J has value 1. And what is our key? What is our key? We know that AI is key. But I is what? It is 2. So A2, go to A2. If this is an array called A, then A2 will be our 10. So it will be key. This I is, the key has become 10 now. AJ is what? AJ, because A is 1. So A1 is 30. So AJ is 30. And AJ plus 1 is what? It is just a number ahead of this 1, 2. That is 30. The number which is coming after 30 is 10. So AJ plus 1 is 10. Okay. So now let's come. We have known the numbers, what I, j, key, aj, j plus 1 will have. And in the next iteration, in next step, as we see that what is with this while will do, we have value. See, these value you are aware, but here next time j becomes 0 because j is reducing. J was previously 1, now it has to reduce. So j is j minus 1, so j has become 0. Aj has nothing, but aj plus 1 is 30. Aj plus 1 is there because j is now 0, so 0 plus 1 is 1. A1 is 30, this number. But aj, there is no number here, so then it is null or empty. right? Again, we formulate aj plus 1, that is key value will be given here, and we know what is the key. The key value is 10, so 10 is assigned to aj plus 1 in this case. Then we again move on to, this has started from 2, it will go to 3 now. This loop will run for 3. I is 3, j is, again we have j as I minus 1, so it will be, the previous value, because this has not worked now. I'm talking about this place. So j has assumed a value 0 from the previous running. J has 0 value, but key is ai. What is ai? A3. A3 is what? 40, right? Again, j is I minus 1, that will be 3 minus 1, that is 2. So it starts from 2. See here, 2 has this j has become 2. Start from 2 and it will go up to 0. So it will run twice. In this meanwhile, we have key value as 40, which we have just found out. And aj is what? 30, aj plus 1, the next value. So 30 and 40. So a2, j is 2. You have to place just this value here and just find out the value from this array. aj plus 1 is 40 because it is the next value of 30. Then what we are going to assign? Key will be assigned to the aj plus 1 value. That is what is our key value? Key is 40. So 40 will be assigned to aj plus 1. Now aj plus 1 is nothing but 40. Now we have to run it again, because we have to run it from 2 to n, and how many values are there? 4. So it will run from 2 to 4. So now we are coming to 4. I is 4, j is retained from the previous step, that is 2. aj plus 1 is 40. So now for 4, what is aj? This ai will be key, so it will be actually our 40, the previous values, right? And now the key will be 20, because a4 is nothing but 20, but a4 is 20, so this key will be 20. J is I minus 1 in the first case, so we'll make j as 3 now. And as we get j, we'll try to find out aj and aj plus 1, and this is nothing but our 40 and 20. And we again do the same stuff while swapping things, and we'll swap this value. Aj plus 1 will be now, this will become 40, this will become 40, because we have swapped. And again we reduce the value of j to 1, that has become 3, then 2, and these values are assigned 20, and aj plus 7 is 30. And again it will go along, because j will run from it was 2, so it will run from 2 to 1, and then coming to 2 to 1. 2 and 1 will be taken by j. So finally j will become 1, and this value will be assigned to 20, this value. Okay, and in this course of actions, these values are arranged just by swapping. If you consider, see, let me show you again. If you are not understanding it, no problem. I'm just trying to tell you that what these are going to do for r and j. So in the first case, let me go back. So what is happening? These are 30, 10, 40, 20. So 30, 10, 40, 20, and here 30 is replaced here. We have changed the value. Then 10 has come here, and then we have another replacement in the next step, if at all it has to. This has become 40, and now this has become 30. Finally, this has become 20 by this simple code. So now finally, after doing all these executions, we have found out an array which is sorted by insertion sort. So insertion sort, if you're not don't get worried about what has happened, because I'm going to analyze this. So what is the precondition of this loop which we have started? First, you have to understand that there has to be some preconditions on this. Then how many times this loop is going to execute? You have to understand that, because number of times these loops are going to execute, the running time will be directly dependent on the run these many times only. So let us understand that this is going to run from n times, means 2 to n, or say 1 to n or 0 to n, but it will run for n times only. This is a for loop. So the effort which is put in here is n only, and we multiply it with some constant c1, and we will not be worried about this constant, as we have seen that we are following RAM model. These constants you can ignore also, but still for the sake of completeness we have to add some constant. So this is n. What about this? As this is going to run n minus 1 times, right? It is going to run n minus time 1 less than this for loop, because at one time this for loop is going to stop. just before that, it is going to run n minus 1 time. Again, this is also going to run for n minus times. What about while? While we don't know, so we assign a t time here. We are not aware. We just place a t time and multiply it with some constant c4. What about this? Again, inside a loop, these two instruction, as we have argued about this instruction and this instruction, these two instructions are also going to run for whatever time while is taking minus 1. So we have placed t minus n minus 1 here, t minus n minus 1 here, right? So why this t minus n minus 1? Because this for loop is going to run for n minus 1 time. So how many times this is going to run? T minus n minus 1 time. Same is true for this. This has 0 time. It is not an executing instruction. What about this? It is inside your for, not while. This is not inside while. This is inside for. So the argument or the reasoning for this instruction, n minus 1 will remain true for aj plus 1 is equal to key. Again, this is not going to take time. What about this t inside this while? What will be the time of this while loop running time? Let us assume it to be t2 plus t3 till tn, where what this t means, ti is the number of while expression evaluation for this ith loop, for any loop iteration. For every for loop, this is going to execute, while is going to execute. So let us add it, that we have just found out. We add all these we add. So C1 n till our C7, we add them, and we have not formulated t yet. So this is actually going to try to combine n and n minus 1 and all those. So ultimately you will find out that it is some constant. See, we are not talking about constants now. This t plus n plus some constant, that is 1, you can say. Then what can this t be? We are not aware of t be, but we have to find out. So this is the best case if inner loop body never executed. If it has never executed, the loop is already, or the array is already in its sorted form. Then we mark ti as 1, because it will never run. We'll say, okay, it will run for constant time. This is a linear function. Then worst case, inner loop body execute for all previous elements, right? Means the loop is, or the array is not sorted, or it is actually reverse sorted. If it is ascending, then the array which is given to us is in the descending form. So it will be it will run for I times, because the upper loop is running for I. So Tn is a quadratic function now. What about average case? We'll not see to this. So we have seen how we can formulate these values. It will be either I or 1. But as I indicated earlier, we are interested in worst case. So let us do some simplification. We ignore actual and abstract statement cost. The order of growth is a measure which is governing our attention. So higher order terms is what counts. The only thing which counts is the higher order term, not others. Means if you have value as n cube, means running time is n cube plus n square, plus say anything else. So we'll not consider n square. It is already n cube. So this is the highest order term. We are not concerned about this n square anymore. So we are doing asymptotic analysis. Please understand that we have to find the upper bound. So as the input size grows larger, it is the higher order terms that dominates. Like this n cube will dominate. N square will dominate, will be there, will be present. But n cube is going to overpower it. So we are not concerned about n square. We will be concentrating upon n cube only. So what is the upper bound notation? We say insertion sort run, the runtime is order of n square. So we should say runtime is of the order of n square, and this order is nothing but big O. We'll always speak this big O as order only. So what is this big O? Fn is order of Gn if there exists some positive constant C and n0, such that Fn will always be less than C dot Gn for all n greater than or equal to n0. This you can understand more formally in this format, that order of Gn is equal to function Fn for all positive constants C and n0, such that Fn is less than equal to Cgn, similar to this one, for all n is greater than equal to n0. Okay, let me make a graph for you so that you can understand better. Now I'm making say a curve or a line. Let me make a line only first. Okay, this is my line and this is my curve, or say it touches here. So this is the point we are talking about, this n0. This n0 is nothing but this point. Above this n0, this function fn, or this, if we call it this fn is order of gn. So this function fn, the below one, will always be less than fn will always be less than this gn, this function gn. Now this function can be anything. Don't worry about the functions. What these functions can be, it may be n square, n cube, whatever, this n log n, whatever functions we are going to study in later sections. This n0 is this. Above this n0, all values or all bound of the function which we are talking about will be governed by the above one. And we say that, okay, this the above one is our upper bound. This is the upper bound notation. Suppose the runtime is n square plus bn plus c. Now we have come to the actual function g and f, and we have been talking, but now let's assume it to be n square plus bn plus n. And a, b, c are, they are less than 0. Replace the constant with its absolute value. We are not worried about the constant. So this value a n square plus b n plus c, this is a function which this will always be less than equal to, let us have a plus b plus c as we add them, and we see that if we combine them, that this will be only 3a plus b plus c n square for all n which is greater than equal to 1. So we assume this to be c dash and let n0 equal to 1. This means this value as 1. So is insertion sort now n cube or insertion sort n? Is it n cube or n? Because we have already n square, so we have to tell and try to underline that if it is n square, the upper bound should be n cube, or we have n here, it should be order of n also. So the big O fact is a polynomial of degree k is of order n to the power k. That means in this case the order is 2. A polynomial which was n square plus bn plus c, the order was 2. So the polynomial of degree k or 2 is order of n to the power 2, that is n square. How? Suppose we have a function here and we just assume that ai is equal to the modulus of bi, and the function will become ak. We have replaced this now, and n to the power k till a0. And when we sum this, we find that ultimately we come to a conclusion that this summation will be only of the constant values, and n to the power k will be the final value which is outside, and these values each and every value will be always less than c into n to the power k. That is why polynomial of degree k is of order n to the power k. What about lower bound notation? We say insertion sort runtime is, this is omega of n, not big O. This is omega notation. So this is lower bound. So what this lower bound says, it says that fn is omega of gn if for all positive constants c and n0, such that this c into gn lies between 0 and fn, for all n which is greater than equal to n0. Let us prove it. Suppose we have runtime is a n plus b, and we assume a and b to be positive, and of course a into n will be less than equal to a n plus b because b is added. We are assuming it to be positive. So we have a asymptotic type bound, right? This one, because we have upper notation, we have agreed the lower bound notation with omega. We have theta also, which is asymptotic type bound. A function fn is this theta of gn if it lies between gn and g2 with some c1 and c2, some constant c1 and c2, right? So in the theorem, if fn is the theta of gn, if and only if fn is both between order of gn and then omega of gn. But proof maybe later, but let me show you now what I am trying to speak. We have a graph. Now this is our function. A function which is above it, which we have agreed with some sort of proof that this function, its actual function is this, is never going to cross this. This is our upper bound, right? And then we have agreed on a lower function that this is never going to cross this, or going to come below this function. This is the lower bound. This is theta, and this is our this is our big O, and this is our omega. And if a function lies between these two, we call it as a theta notation. See, it is lying between these two. This is the practical complexity, how it varies. First of all, this one, first one. This is nothing but this black one, right? Or it is blue, if you can see it. This is log n, okay? Then this function is n. This is n log n. This is n square. This is n cube, and this is 2 to the power n. This is this is n cube, and this is 2 to the power n. So now, as these value increases, the number of inputs increases. As the number of input would increase, the function varies like this. Initially, if you see, they all vary similarly. But as the value increases, we see that n is, log n is quite good. It has not changed invariably. While this one, 2 to the power n, is doing some serious damage to the complexity. These are, as we go to value number 500, this is for 250 values, this is for 500. Now this is approaching, and the previous one, n square, has now come down, but others have somewhat remained the same. But this one, this we are concentrating upon, 2n, is actually going or bending towards this n cube. And what about 1000? 1000, this log n has approached x-axis so near to this order of n, but this 2 to the power n has actually crossed the n cube value. But 2 to the power n has a bit more worst implication as the number of size would increase. So these are the values up to 1000. It is okay. You can assume 2 to the power n is less than n cube. But when we go to 5000 and sort, this 2 to the power n has actually overpowered all others. While these values, these functions have remained or are very critical to us, because we want our algorithm to assume these values, say order of n, log n, and n log n. So best one would be our log n, and then likewise in increasing order. And this is the practical complexity, because we are not dealing with 5000s. We are dealing with these numbers, maybe more than these numbers. So this is how they are variating. So we need to concentrate upon these values. Actually, it goes to n square. And complexity increases like this. So these ideas, or the ideas of the functions, should be very clear to you. Which function should have greater complexity in the long run. We have other asymptotic notations also, like this is small o omega, small o game omega, and others. So a function fn is big O, small o, we can say, out of gn if for all positive constants cn n0, such that this cn is actually less than, or f function is less than equal to cgn. This is greater for n greater than equal to n0. And what about omega gn? This cgn is fn is the upper bound of this cgn. So, or if you assume it like this, if we are not aware, or we don't consider this to be practically understandable, then just consider that this big O is like less than equal to, and omega was greater than equal to, and theta was actually is like, which is equal to, while these two which I introduced just now they are less than or greater than. So this was our second installment, and we have tried to introduce some functions. If you are not well aware of this, I strongly recommend you to follow some text, because this is very important. Otherwise, our next sessions they'll be containing all these in everywhere. So we need to concentrate upon this, because they decide our language or program complexity. Thank you so much. Take care.